All right, I think we are ready to continue now. So hopefully you enjoyed that video by Professor Rajagopal. And he was discussing how the magnetic flux, right, as the magnet is falling and it uses like a magnetic flux in like the circular cross section of the pipe, right? There's a current there. And so this current is going to create a countermagnetic field. And that's exactly why the magnet slows down within the pipe. So that's one of my favorite examples of Faraday's law right there. And so on the left of the two equations, you can see the first one is like the simplest form from like AV Physics 2. And then the one below it is more of like on a college-based level.
Right, so we're going to talk about some application of the Faraday law we just learned, and also this application called SQUID will combine what we learned in quantum mechanics as well. So it's a device that's used to measure magnetic fields. So this slide, we have some places where it's used. So the left one is the South Pole Telescope, and we have some link to the information about these about these cool telescopes. And it can also measure. It's so precise that it can detect the very minuscule brain waves. Yeah, so the South Pole Telescope has some 12,000 SQUID detectors. So it's very accurate, and it can detect candidates for dark cold matter, a particle called axion. Yeah. So yeah, this is a basic illustration of SQUID. It's an acronym. It's called a Superconducting Quantum Interface Device. And we are going to talk about what each of these means. So you can see there's conductivity relates to our ENM, and quantum and interference. Yeah, it's interference, my bad. So it's related to the Young's double slit experiment we talked in the first lecture, and yeah. So first we're going to talk about superconducting, and this part is tied into the quantum property of it. So if you look at the graph on the left, this is a squid, and it's a wire, but it has a loop in the middle. So it basically separates into the upper half and lower half, and see there's a circle. And in the middle, the gray part is called a Josephson conjunction. So what we do is that this entire device is in a superconducting phase. What it basically means is that it has no resistance, and if we put current through it, it'll flow forever. And the Josephson conjunction is not superconducting. So what this causes is that electrons have to tunnel through the conjunction. If you remember these two graphs about quantum tunneling, so because we talked about matter wave by de Broglie, so the electrons can tunnel through while losing some kinetic energy. And what this gives is a quantum effect. Next slide. So if they tunnel through the Josephson conjunction, some interesting things will happen, such as there will be alternating wave in this conjunction. And so basically current can change directions, and voltage will relate to the differences of current. So since current is also alternating, it's basically oscillating between these different positive and negative numbers. And through complicated math, so the voltage of across the Josephson conjunction will gives us the differences of these. And if you don't know what currents or voltage, it doesn't matter because we don't need to really look at them precisely here. It's not like what we learn in AP Physics C anyway. So Yeah, it's we're basically looking at the quantum effects here. And what end up is that voltage can give us the frequency with the which the current oscillates. Yeah. And here's Ampere's law. We also need Faraday's law, which we just learned. And then very important thing is a right-hand rule. So we don't need to worry about the laws here, but we can look at the right-hand rule first. It tells us the direction which in Faraday's law a flux will be induced. And here, if we have a wire with a current, we hold our right hand and grab and point our thumb in the direction of current. Our fingers will wrap in the direction of the magnetic flux, magnetic field that it creates. And same thing if we, for graph B, if we wrap our fingers around the current, we will get the direction of the magnetic flux. Yeah, it's it's basically an illustration of cross product. Yeah. Yeah, so now we can talk about SQUID. So if we have this SQUID, right, and it has some current running through it, we want to detect magnetic flux with it. So we put a magnetic flux through the middle. Usually the currents will split in half, and that's in physics C, but basically current splits and half goes in the upper half and half goes in the bottom. If we have a magnetic flux, it will induce a current because of the E&M Maxwell equations. And on the left, there's a J, and that is the current induced. So on the slide, it says the current here is not induced by flux, rather the current produced adjustment on flux. So the current is producing flux, and what it does is that it quantizes the original flux in the middle. So you have some flux in the middle, but this SQUID device, because it's in its superconducting state and it can produce alternating currents, if the total flux in the middle, it has some property of like a flux that is larger than a quantized value, because as we discussed previously, all of these values are quantized, so you have to have some integer number value of a very small unit flux. And if it's the end of the flux is larger than this half value of the quantum of flux, it will induce a current that adds on to this flux. So in this case, it'll um, give a, positive flux to add on to basically round it up to the upper integer. And if it's smaller than half the quantum value, it will produce a negative flux to basically trim off. So you can see as flux increase, we have two graphs on the right, the current would adjust and the total current IC will oscillate. And yeah, next slide, please. So that is how it measures flux, so or magnetic field. So if we observe, because current is oscillating as flux increase, it will oscillate, and you can see on the very top left, because SQUID tells us how the voltage tells us how current oscillates. We can graph this current voltage versus flux, and um, when it's zero flux, the current would be that line. But if you get um, a a certain flux, it will go down and it will also go up. if it's increasing and oscillates and so on. And the voltage has that relation to currents. So we can also graph voltage to flux, and we get this sinusoidal wave that is oscillating. And this ties us to like a really close observation to Young's double slit experiment. So in Young's double slit experiment, if you remember, it was oscillating between these different wavelengths. And here the voltage is oscillating because it's adjusting according to like rounding up the flux to its next quantized value or trim it off. Yeah, so it's a pretty cool thing. So to sum it up, or also at the end, so we can detect total flux because each uh, each period of those flux versus voltage value, the period is one quantum of flux. So that's how precise we can go. We can count these period and we can know the total flux, what it is. So yeah, it can help us a great deal in measuring small flux, small magnetic fields. So to sum it up, we went through the quantum tunneling and Josephson effect and Ampere's law and right-hand rule, also Faraday's law. Also, there's actually you don't have to worry about those laws for now, and we will probably discuss more quantum mechanics and ENM in the next semester. And there's quantization and double slit interference.
All right. So to continue, we have like we worked on the railgun project last year, and so one inspiration for that was this image right here. There was a video about this, and this was like the military that they had the railgun here. And so we were looking through some resources for our project, right? And so we were thinking about like the right-hand rule. We were also thinking about currents and like the electromagnetic forces that are being generated by those currents, right? And so you can see from this picture here, we have driving currents, armature current as well. And so it's showing like the armature and the projectile, right? And how a projectile can be launched via a railgun. And so one key component of that is using the right-hand rule to see the direction of the direction of the electromagnetic force, the magnetic field, and then the electric current as well, right? So you guys can try this with your hands at home. And so it essentially says that if you have like two of these, like you have current or field, then you can find the force, right? If you have like force or magnetic field, then you can find the current, for example, right? That's the principle behind the right-hand rule. And so it's about finding like perpendicular vectors, right? So if you have like these two vectors, the field and the force, then the current is perpendicular to those two, right? If you have like force and current, then field is perpendicular, right? So that's what the cross product is about. It's about finding the perpendicular vector. And so we had some calculations regarding this. These ones are specifically by Andrew right here. You can see they're the idea of like the rails. And so in Mr. Nauman's room, we still have like the conductor, the capacitor. We have the capacitor there. And so we were able to use the capacitors. They have like very high capacitances to be able to try and launch the projectiles. But one problem that we were having was like the friction with the projectile on like the rails of the capacitor. And so you can see that the final value that Andrew came up with was 0.411 Tesla, which is many times stronger than like a fridge magnet, for example. It's a very strong magnetic field. So we'll elaborate a bit more on that later, but for now we're going to end off the semester with a Kahoot. So I will quickly begin that.
Actually, I can share here. All right. So here's the code. Okay, everyone please join. So this Kahoot will be some pretty interesting photo from the Physics Photo Contest. They're the same, they're offered by AAPT, the same organization that offers, I think, a physics ball and F equals MA. So, and it's coming up, you should register. And we have sent out an email about that. One more. I think we're short on time, so let's start. It'll be a 10-question Kahoot, and each question is pretty fast. Yep, this is a term. So we have a cloud chamber with vaporized alcohol to demonstrate ionization of ionized. Oh, so it's a glory? It's a different term, actually. Yeah, so take a guess. Yeah. Yeah, I guess the main is actually gravity pulling the water down is rather than adhesion. So they name it this way. Nice. So turning to droplets, making it very small, and so it condenses fast because it can find particles in the air to condense around. Yeah, refractography, it's a different using lasers and such to refract. Yeah, it's pretty cool, but it's not refractography. It's just a simple refraction. Yeah, nice. No one likes the third one. I think it's pretty cool. Yeah, so that is. Right. Nice. So those are all image from the physics photo contest. Hopefully that gets you guys excited and give you some inspiration. Nice. So it's been a great semester. All right. That is the last of our meeting, and hopefully see you guys next semester. Yeah, have a great break and good luck on finals. Yeah.
Right. So this was the last meeting of this semester.
Yeah.